Hello, everybody. Welcome to class. Hopefully it is going well for all of you. And let's see, I know most of you, majority of you, I should say, are in, oh gosh, I think Rodemacher's class. And where do we find the poll? Good question. I don't know. I can see it here. And maybe if you go to the bottom of the screen and you click on there might be something that says polling. There is on my screen, but I don't know what your guys' screen looks like exactly. So if anyone else wants to join us on video, that'd be great. I got the poll the first time I logged in. Okay. Hey, Eric. Hey, Teresa. Good to see you both. If the poll doesn't pop up for you, don't sweat it too much. It'll be fine. I was really just trying to get an idea of what you guys wanted to see today. I watched, what's his name, Simontel Rodriguez's class earlier today, which a couple of you are in, and he seemed to be talking mostly about level curves, which I can definitely talk about today. And I know I've looked at some of the stuff from Rodemacher. I think I'm saying his name right. I don't really know. And looked like his notes covered a lot of the multivariable kind of functions and domains and things like that, as well as looked like he was moving towards talking about limits. But actually, I have his notes somewhere over here. Actually, I have his notes right here. Yeah. So anyway, I was going to talk about that kind of stuff, and I feel like. What do I feel like? Let me look for 1 second over here. Also, if you guys have specific questions you want to ask, I'm always happy to work on things like that. Yeah, he was definitely talking about functions, two variables. He talked about level curves too. We should definitely talk about level curves. All right, let's do some level curve stuff. So level curves kind of more generally is part of, I would say it's part of your graphing process. It's also, God, there's a lot. Level curves have a lot that kind of go with them. One of the other things I want to say about level curves that we'll see later on is that, so if you've ever looked at like a contour map of the world or like a geographical area, those curves you are seeing are level curves because they are lines that represent one particular height of the surface. So I feel like it's probably easiest to just do this with an example. So let's look at, see what have I got here. So I want to do one that's kind of different. Yeah, I'll do this one. Let's look at the function f of xy equal to 9 minus x squared minus y squared. It's kind of one of my favorites, but we'll just learn this as well. I do want to remind you, if you've got questions, you want to say something with your mic. Not that I won't look at the chat, but I'm less likely to see the chat when I'm up out of my chair. So feel free to chime in anytime. And I would encourage everyone to chime in just in general. I would like to hear your voices. You know, it's lonely in this world right now. So, so let's talk about how, well, we'll talk about level curves. I'll talk about the graphing of this because there's a little bit more involved. So level curves. Level curves are basically when you just set the function value equal to a certain number, and then you try and see what the two-dimensional curve looks like. To be able to do that, though, we have to make sure we're actually picking numbers that are in the range of this function. So before we talk about level curves, we might want to look at the domain and the range real quick. So domain, I think, is pretty clear. There's no restrictions. X and Y can be anything. So the domain is all coordinate pairs, if you like, in the xy plane or in R2, or all of R2, however you want to say that. The range, on the other hand, well, again, we're seeing this common theme of getting an x squared and a y squared. I see this not as a negative x squared minus y squared. I really think of this as 9 minus the quantity x squared plus y squared. So if I'm looking at, and I'm going to write it as z equal to 9 minus x squared plus y squared. I'm not trying to do a ton of work here. I'm just trying to think about, okay, I know x squared plus y squared is always positive. So 9 minus, or sorry, I should say non-negative. 9 minus something that's non-negative, this is always going to make this whole quantity equal to or smaller than 9, right? So if these are both 0, you're going to get 9 for z, and then any larger values here is going to make this whole thing smaller and smaller. So the range here is looking like everything from negative infinity up to 9. That's our range, right? Because if any x and y are anything other than 0, the values are going to get smaller. So the reason I mentioned the range is because our level curve values, we can only pick values that are in the range. If we pick something like 10, we would get no solutions. So let's start with z equal to 9. Well, I'm going to use different colors. Smart. Okay, so if z is equal to 9, my equation is 9 equals 9 minus x squared minus y squared. Now, actually, I'm going to back up just a tiny bit. Instead of picking z equal to 9, I'm actually just going to pick, usually use c for some reason. I'm going to pick z equal to c, and then solve for this equation, c equal to 9 minus x squared minus y squared, to make it a little bit more manageable. Sorry, I keep writing the wrong thing here. What it really is, I'm going to bring x squared plus y squared over to the other side. So I'm going to really write this as x squared plus y squared equal to 9 minus c. And the reason I do that is because then it's really, really, really obvious that this is going to be a circle of radius, whatever the square root of this number is. So for example, and let's use some different colors here. When c is equal to 9, I'm going to get x squared plus y squared equal to 0, which is kind of a dumb level curve. It's the circle of radius 0. Not too exciting. It's just the origin. Okay, but now I'm going to pick a different value. I'm going to pick something in the range, which means I got to pick something smaller than 9. So let's pick like c equal to 8. For c equal to 8, I'm going to get x squared plus y squared equal to 1, which is a circle of radius 1. So go over 1. And often we label our level curves as we draw them. So this is c equal to 1. And then I'm going to pick values that are convenient for me. I'm going to pick c equal to 5. So c is 5. I'm going to get x squared plus y squared equal to 9 minus 5, which is 4. Which is a circle of radius 2. And then I'm going to do one more, maybe 2 more. I got more colors. I'm going to do c equal to 9. Sorry, c equal to 0, which is going to give me x squared plus y squared equal to 9, which is a circle of radius 3. I feel like I made a mistake somewhere here. Oh yeah, I wrote 5 here and 2 there. Especially if you see mistakes, you should speak up with your voice. And then c equal to 3. Sorry, not c equal to 3, c equal to 0, circle of radius 3. Something like that. Oh, no, that's not the best circle I've ever drawn. Sorry.
Wait, James.
And then finally, question.
Yeah, for the circle labeling, shouldn't the red circle be labeled as c equals 8?
It definitely should. I made the same mistake there too. Sorry.
And then, yeah.
It should be c equal to 8.
And the green circle should be c equals, is it 0 or?
It is 0.
Okay.
Yeah. So here's what I'm getting from this information. At the highest height, which is c equal to 9, the circle is really tiny. And then as the c values, the z, which are really the z values, get lower, the circle gets bigger, right? 8 circle, and then c equals 5, bigger circle, c equals 0, bigger circle, and then I'm going to do one more. C equal to -7, which is going to give me x squared plus y squared equal to 16. That's going to give me a circle of radius 4. So those are, oh shoot, darn. I meant to, sorry, I gotta pin my video here. It's not a big deal for you guys right now, but if you watch the video later, if I don't pin my video, it'll show up super small for everybody else. So that, now it shouldn't be terrible later on if you decide you want to watch the video again for some reason. So these are the level curves of this graph. Some of them, I should say. And they kind of, right, they allow us to visualize what this thing looks like. So if I'm thinking about this as a topographical map, this is the tallest circle, and then this circle that's wider is lower down, this circle is lower, this circle is lower. So I'm going to try and draw it in 3 dimensions. This is always a challenge. Let's see, okay. So I know, come on, red pen. So let's say this is 9 up here. That's the point 0, 0, 9. I've got a circle of radius 1 and then go down 1. So, all right. I want to try and just draw these little curves each and then connect it all, but that's not really the way I would draw this. The way I really draw this is by using what's called a trace. So level curves are curves you get by setting z equal to different things. The traces are the things you get in specific planes. So if I were to set, say, sorry, this is x, y. Let's see. If I were to set y equal to 0, I would get z equal to 9 minus x squared, which is a downward opening parabola. Hits at 9, has x-intercepts of 3 and negative 3. In a similar way, if I set x equal to 0, I get z equal to 9 minus y squared. Again, a downward opening parabola, has intercepts at 3 and negative 3. So what I'm really thinking about drawing here are these downward opening parabolas. This is in the YZ plane. That's the point 0, 3, 0 right there. And then the same thing along the ZX plane. The ZX plane is always challenging to draw in. And then, where did I get there? And then here are my level curves. So up here, oops, not in blue. So up here, right, there is my C equal to 8 level curve. And maybe like, I don't know, maybe about here-ish. There's my C equal to 5 level curve. And C equals 0 is obviously the XY plane. And when you get the circle of radius 3, it's gonna, and so again, it's where your drawing skills are more important than I wish they were. There's my circles don't quite look like they're in the same perspective, but there you go. C equals 0. And then I can draw one more down low that would be C equal to negative 7. So that's kind of, that's the idea of what these level curves are, is that they're just saying, I'm taking a horizontal slice through space and seeing what I get from the curve. And the horizontal slice can be at different heights. And since we can't have a 3-dimensional 2D graph, right? Like this is kind of supposed to be, oh, like you're supposed to be able to read this and be like, oh yeah, it's gonna look kind of like that. Questions?
Question? So for my professor, Professor Rodriguez, he mentioned something about there are some graphs where it's difficult to draw the horizontal cross sections, and you might have to set one of your variables to be a constant.
Yeah.
So,
and so that's actually what I so let me give you another example, one that's similar to what he did in class today. Yeah. So yes, let's talk about. Sorry, this is going to be fun each time. Okay. So kind of a classic example, which he did either this one or one like it, is the multivariable function y squared minus x squared. And so the the difficult thing about this particular example is that if you start picking different level curves, you're going to, or the different values for level curves, you're going to get hyperbolas, which are not everyone's favorite thing to graph. So like if you set c equal to 1, you're going to get y squared minus x squared equal to 1, which, yeah. So if y squared minus x squared is equal to 1, y can be 1, x can be 0. So you have the point 0, 1, and 0, negative 1. Right? Y can be 1 or negative 1, x can be 0. And then if the y values get bigger, the x values can get bigger. So like y can be 2 and x can be the square root of 3. So I know it's kind of funky. 2. Sorry, I'm just doing the probability, the hyperbola the other way. Yeah, so it looks kind of like this. My hyperbolas never look really great. And this should be symmetric about that here. Kind of look like that. So there's that one. And then if you draw more of them, so like if you do c equal to 2, you're going to get y squared, y squared minus x squared equal to 2. And then your intercepts, instead of being 0, 1, and 0, negative 1, you're going to get intercepts that are, well, if x is 0, y can be plus or minus the square root of 2. That's like about, if that's 2 there, it's like there-ish. And it's got a similar kind of shape. But the thing is, you can also pick negative values. If you pick, let's use some different colors. I'm using all the colors today. If you pick c equal to negative 1, then you've got y squared minus x squared equal to negative 1, or x squared minus y squared equal to positive 1. Right, it's multiplying everything by negative 1, which is a hyperbola that's opening along the x-axis instead of along the y-axis. So that one, and this is where my graph, unfortunately, because I don't think these actually cross over each other, but they kind of look like they will. So here's this hyperbola, which doesn't look wonderful. And then if you let c be more negative, like c equal to negative 2, it would look something more like this. And so if we think of the red as the highest up part, and then blue is the next highest, and then orange is the next highest, and then green, it doesn't really, I don't feel like that, reading that shows me the shape of the thing very well, right? It's hard to see it. So also if you let c equal 0, you're going to get y squared minus x squared equal to 0, which is just y squared equal to x squared, which is the line y equal to x and y equal to negative x, which looks like that. It's kind of super funky. Not a very helpful grouping of level curves if you haven't seen it before. Like I can kind of see it as like, oh yeah, I know I've got like hyperbolas there and then close hyperbolas and this weird thing and then other stuff the other way. But graphing this is really better done by, well, using what most people call traces. So your professor did say you can set other variables to be constant values. Typically the choice we're going to make before we make any other choice is to choose 0. So I'm going to erase this because I need the space. So obviously later on, if you want to look at this again, you can pause the video. Yeah, I wonder, you could probably even take like a screenshot of it if you really wanted it to still be on your computer while we do stuff. Probably, you might be advanced to do that, I don't know. So the way I would actually graph this thing is by doing 2 or 3 things. I'm going to set, so I'm going to think of this as z, and I'm going to set x equal to 0. When I set x equal to 0, that means I'm working in the yz plane. Actually, let's, yeah, sure. So again, this is the positive x-axis, this is the positive y-axis, this is the positive z-axis. And when I set x equal to 0, well, it's easy to see what happens. I get z equal to just y squared, which is easy for me to graph. So I'm in the yz plane, right? Because if x is 0, it means I haven't moved out towards you and I haven't moved back away from you. I'm just in this yz plane that I'm thinking of being as the plane that the board exists on. And in that yz plane, I'm getting, sure, probably should use a different color. Oh well. I'm getting that parabola in the yz plane. And now, if I set y equal to 0, I'm going to get z equal to negative x squared. And that's in the xz plane, which is kind of like the plane that's coming straight out at you. Like, actually, there's some paper here. So, if you want to think about it this way, this plane here, this flat plane in 3D space is the xy plane, right? When z is equal to 0. This plane here, the one you can kind of see full front on, is the yz plane when you haven't moved forwards or backwards. And then this plane cutting at your face is the xz plane. The one that, well, actually, I should say in front of the camera here, right? It's the one that's like straight out at you. This paper is not as firm as I would like it to be. That's your xz plane. But usually we've got it more tilted so we can kind of get an idea of what things actually look like. So I've got z equal to negative x squared. That's a downward opening parabola, so it kind of looks like this. Okay, so now what the heck is going on? Well, this is a saddle. Whenever you have a parabola opening upwards in one direction and a parabola opening downwards in another, it's a saddle. And there's a number of ways you can draw this. It does take some practice, but here's what I'm going to think about. I'm going to think about, I know up here above, I have hyperbolas opening along the y-axis. Let me double check that. Oh, I erased them. I was looking at the other side. No. So I have hyperbola opening that way and a hyperbola opening that way. And down here, I have hyperbolas opening along the x-axis, which I'm not going to draw just yet because I really want to do, I can do that, fine. And I would have one back here as well. And then if we connect things up, you can kind of see, this one always screws me up over here. You can kind of see part of the saddle, right? It definitely looks like a saddle. You can imagine someone like sitting there with their legs over either side of that thing. It's called a saddle for a reason. Also, if you've ever done any hiking up mountains, there are things called saddle points on a mountain where you hike up and you can either stop here at the top of the saddle and keep going over the hill, or if you change directions, you can keep going up towards the different summits. So the level curves for drawing this one aren't super helpful, but the traces where you set x equal to 0 or y equal to 0, or even setting z equal to 0, all in this case is not particularly helpful to set z equal to 0. Those are called the traces. And those really help you kind of get an idea of what the graph looks like. What else to say about this one? Something I think we'll see in this class is that, there are kind of three kinds of critical points. So, in 17a, when we talked about like a max or a min of a function, well, we can talk about that in 3 dimensions as well. We're not there just yet, but besides the max and the mins, you're also going to see there are saddle points. So sometimes you have a saddle, which is a minimum in one direction and a maximum in a different direction. And then sometimes you have a tight board is what you have. Sometimes you have a point that's a maximum. That's higher than all the things around it. So we're definitely, I think definitely going to see a way to classify relative extrema for three-dimensional, for functions of two variables. Okay. Also, I've got a One sec here, come on. Sorry, my computer is being challenging at the moment. Come back, okay, where do we go? 1 second here. I have a really good picture here, one moment. Oh, there we are. Sure. So I'm going to share my, I'm going to end the poll. I'm going to share my screen, I think. Yes, cool. Okay. Close the poll. Just wanted to share this with you. So this is on Grant's webpage. I think it's under the 17C stuff, but it might be under the 21C stuff. And here's his picture of the same saddle that I just drew. You'll notice he also drew some of the other curves, or I guess they're traces, where you're setting like right here. He drew, I can zoom in, right there, he set y equal to 1. So if y is equal to 1, sorry, this is the wrong picture. Right? Over here, if y is equal to 1, he's getting the curve z equal to 1 minus x squared. So it's a little bit higher up, so it's looking like this. Right? You're getting that parabola there. And he did that over here as well, right? Over here, he set y equal to -1. And still got z equal to 1 minus x squared. So you can definitely draw more curves to help you kind of graph a thing. But it really kind of unfortunately comes with practice. Now let's zoom back out. Yeah. Yeah, I think this is on Grant's current. So actually, just as an aside here, if you want to look at Grant's web page, this is where I steal. I borrowed. We're friends. Grant surfing. I borrow a lot of things from Grant. So I was just looking at his various level curves, and there are all kinds of cool examples. So yeah. Anyway, lots of good stuff. So right here's the same sort of picture over there. I'm pointing at my screen like you can see me. Oh, I can't. I'm seeing me anyway. Over here, you can see the same picture of level curves I was trying to draw. And here is the style that goes with it. And you can kind of see, right, like up here at the top, you can see the level curve where k is equal to 2, or I use c, use k. And here's k equal to 1. And here's k equal to -1. Here's k equal to, wow, this is a good picture. Great. Some good pictures. I'm jealous. All right, anyway, let me get out of the sharing here. So, yes, there are definitely lots of good resources. Grant's website is one of them. I use it all the time. All right, should we do another level curve example? Yes, no, maybe so. I see some yeses. Okay. Let's see, what other kind of thing can we draw? Let's go over to.
I think James.
Yeah.
Or Rodriguez, he also showed the difference between for some of the level curves. I think there was one where I forgot which one it was at the top of my head, but it was a cone versus the paraboloid.
Oh, sure. Yeah. And that really just, I mean, yeah, we don't like that for sure. So, yeah. So here are two different functions. F of xy equals to x squared plus y squared versus f of xy equal to the square root of x squared plus y squared. So they look very similar. They are very similar. The difference between them is actually just what you're saying. One of them is a paraboloid, meaning like a parabola, but rotated around. One of them's a cone, meaning it looks like a straight line rotated around. And again, the hard part here is so level curves are useful, like they give us information, especially, in fact, yeah. Let's draw level curves because they do tell us something. So, okay. So we're going to do, C equal to 0, C equal to 1, C equal to 4, and C equal to 9. Sure, let's do that for, we'll do that for both of them. One of them is probably going to turn out terrible. So here, let's just draw it. If I'm setting this equal to 0, I'm getting the circle of radius 0. I'm setting this equal to 1, I'm getting the circle of radius 1. 4, radius 2, 9, radius 3. And level curves are concentric circles. And so one way you can think about this is if you're traveling right along the surface, the faster you cross level curves, the steeper your ascent is. So if you just travel along around a level curve, you can always stay at the same height. If you cross level curves, you're going to go up or down the surface. And that's why if you look at, like, again, I can't remember the name now, a map that has level curves, there's a better name for it, a something map, anyway. The closer the lines are together, the steeper your climbing is going to be. So if you're actually like using one of those topographical maps to navigate outside somewhere, and you're trying not to like climb up the hardest hill ever, you're like, oh, I'm not going to go that way because I'm crossing too many lines. You go the way that kind of goes up them more slowly. So these are the level curves: C equals 1, C equals 4, and C equals 9. Whereas over here, things are going to get a lot bigger. And I might have drawn, so this might be, so, well, we'll see. So if I let C equal 0, I'm still going to get the point 0, 0. If I let C equal 1, I get the square root of x squared plus y squared equal to 1, or x squared plus y squared equal to 1 squared. So I still get a circle of radius 1. But now when I let C equal to 2, sorry, not 2, 4, I get the square root of x squared plus y squared equal to 4, which gives me x squared plus y squared equal to 4 squared. So this is a circle of radius 4. So at the same height, this circle over here is going to be much, much wider than the circle over there. Oh boy, okay, sure. That's a circle, we'll pretend. Yeah, it's kind of a circle. So right, so these curves have the same, these are the same circles, right? These surfaces look the same at a height of 1. But at the height of 4, this circle is much smaller than that circle. Because this cone, the cone gets wider much faster than the parabola gets wider.
Okay.
Now, I wouldn't draw either of them this way. Go ahead. Okay. Like, not that this isn't useful information, but so what this is telling me so in fact, for the cone, you can actually fill in the inner parts, right? If you say, oh, if C equals 2, that's just going to be a circle of radius 2. And if C equals 3, it's going to be a circle of radius 3. So we're getting the same circle radii, but at much lower heights. I'm going to try and draw these next to each other so that you can kind of tell the difference. Good picture. I like drawing saddles. Okay. So the nice thing about the cone, the one that was, yeah, in red, f of xy equal to the square root of x squared plus y squared. I know how to draw this. I know, in fact, what I'm really thinking about is the trace of this. I'm thinking about, okay, if I set x equal to 0, I'm going to have z equal to the square root of y squared. which is looking like z equal to the absolute value of y. Right? Remember when you square root a square, it's not just the thing, it's the absolute value of the thing, which is why I'm getting z equal to y and z equal to negative y. And then if I let y equal to 0, same idea. I'm going to get z equal to x squared. So in the xz plane, I'm getting, God, I don't want to draw that. Sure. So here's c equal to 1. Sorry, driving is always challenging for sure. So there's equal 1. We go up higher. The nice thing about the cone is the height is whatever the radius is. So there's z equal to 2. And you can keep going. On the other hand, the paraboloid gets bigger much slower. Oh, it gets bigger, slower, bigger, faster. I guess it depends on what you're thinking about. So we still get the same thing happening at, and again, I'm not even trying to draw a level curves and draws. I'm really just saying, I know I look like parabola, right? I'm looking at f of x y equal to x squared plus y squared. If I let x equal 0, I get z equal to y squared, which looks like this. And if I let y equal to 0, I get z equal to x squared, which is always harder to draw, but it kind of looks like this. And my level curves are still circles. They just don't get as big or as wide as fast as these circles do. So at a height of 2, my circle is only at a radius of square root of 2. So these level curves, the circles of radius 1, 2, 3, 4, 5, etc., are all spaced out evenly. These level curves of radius 1, 2, 3, 4, 5, etc. are not spaced out evenly, right? The spacing on those, right? These ones have, this is a circle of radius 1, 2, 3, but the level curves are at 1, 4, and 9. Whereas these level curves that have a radii of 1, 2, and 3 are at 1, 2, and 3. So that's kind of the difference there. Again, that one's called paraboloid because it's just a parabola revolved around. This one's called a cone. Any shape that you kind of just revolve around an axis, you often put an oid at the end. Like if you take an ellipse and revolve it around, it's called an ellipsoid. If you take a circle and revolve it around, it's called not a circloid, it's a sphere. But yeah, we don't have a lot of time. Never enough time. Okay. So one more shape. And you might see. No, you probably won't see this. I should not do that example. That's a bad example. Yeah. Let's do some other things with the limited amount of time we have left. See, I forgot what else. I closed the poll after I asked you guys to do it without really looking at it. Brilliant. So I do feel like it would be worth your time to, yeah, let's look at a couple examples of, did I do that one? I didn't do that one. Sure, so let's look at this example. Let's do some multivariable limits. Limit as x comma y approaches, what do we got here? I don't think I did this one on video already. Yeah, 2 comma 3 of 3x squared plus xy minus 2y squared divided by, we got here 3x minus 2y. And a lot of the time, you're going to have, most of the time, these multivariable limits, we're going to have 0 over 0 limits. It's not particularly exciting if it's not 0 over 0, you just plug it in and you're done. It's not 0 over 0. But here, we definitely have 0 over 0, right? If I plug in 2 for x and 3 for y, definitely get 0 on the bottom, 6 minus 6. I plug in 2 for x and 3 for y on top, I definitely get 3 times 4 is 12, plus 6 is 18, minus 2 times 9 is minus 18. So I get 0 over 0. And what to say about this? So what to say? Well, if I'm going through a point and it's not 0 over 0, not always, in fact, not in the next example, but a lot of the time these limits exist. Not always. But a lot of the time, you're looking for something to factor out. Specifically, I would really love for this 3x minus 2y to factor out. It's kind of like how if you're doing the limit as x goes to, I don't know, 4 of, make something up, x squared minus 3x minus 4. Right, here you're looking for an x minus 4 to factor out of the top and the bottom, because plugging in 4 is what's making things 0. So if you get rid of an x minus 4, you totally, sorry, this is a 0 over 0, right? If you plug in 4 on the top, you get 16 minus 12 minus 4, 0 on the bottom. But if you can factor something out, like, well, on the bottom, I can definitely factor out a 2 and x minus 4. On the top, I can definitely factor out that. And you can cancel those, and then you get the limit of the rest. You get 5 over 2. Same kind of logic is going to apply here. Since we're getting 0 over 0, we really like to be able to factor out something that's easy to deal with. I really think I might be able to factor out a 3x minus 2y from the top. I'm actually not positive because I haven't done this problem yet. We're going to find out together. So use an equal sign because it's equals. So on the bottom, I've just got 3x minus 2y. On the top, well, I know I'd like to have a 3x minus 2y. But then if I have a 3x, I'm trying to get a 3x squared, I need an x there. If I have a minus 2y, I'm trying to get a minus 2y, I need a minus y there. And I have to hope the middle terms work out. I get a minus 2xy. I do not, I made a mistake. I need a plus y there. So I get a minus 2xy plus a 3xy, which gives me 1xy. So that is how this factors. And then I can cancel. And then I can say this is equal to the limit as x comma y approaches 2 comma 3 of x plus y, and just plug in 2 for x and 3 for y, and get 2 plus 3, which is 5. And I will say a lot of the time, not always, if your x, y is approaching something that's not 0, 0, a lot of the times the limit's going to exist. But not in this next example. Yeah, Teresa.
In the textbook, I saw that they were taking the lines and they had a graph where it was like the limit approaches a different direction, and it says that if it approaches like on this certain line but in a different direction, the limit doesn't exist. So
exactly.
What does that mean?
Sure. So here's what that means. That's not good. So in 17a, you probably saw this limit. The limit is x goes to 0 of the opposite value of x over x. Maybe. But here's how it works. It doesn't exist. And the reason why it doesn't exist is because the limit from the left and the limit from the right don't match up. So if you approach x from 0 from the right-hand side, well, if x is positive, the opposite value of x is just x. Right? Right. And then x over x is just 1. So the limit as x goes to 0 from the right of 1, which is 1. But the limit from the left of the absolute value of x over x is the limit from the left of 0. Well, if x is negative, then the absolute value of x is negative x. Which means this simplifies to the limit as x goes to 0 from the left of -1, which is -1. And these don't match, which means the limit doesn't exist, so the left and the right-hand side aren't the same. Here's the graph as well. There's what that function looks like. The left-hand side is approaching -1, and the right-hand side is approaching +1. And since the left-hand limit and the right-hand limit don't exist, they're not the same. The same thing is true for multivariables, except that you don't have just two directions, right? If you're trying to approach the point 0, 0 in the xy plane, you can come from any direction.
Oh.
So they're saying, just like here, if two different directions have a different value for the limit doesn't exist. The same is true here, but there's an infinite number of directions we can choose from. So with the few minutes we have left, I think I can throw an example at you guys to find it. Okay, there we go, sure. So let's look at this one. Kind of starting to, I have to wash my board today. So let's look at the limit as x comma y approaches 0 over 0 of, where'd you go? 8x squared y over x to the 4th plus 3y squared. And before I just give away the answer, let me tell you some popular choices. So here are a number of paths that go through the point, I should say through 0, 0. Y equal to 0. Horizontal line goes to the origin. X equal to 0. Y equal to x. Y equal to a multiple of x. X equal to a multiple of y. Y equal to x squared, or y equal to any power of x, or y equal to a multiple times any power of x. And vice versa, x equal to y squared, or x equal to y to any power, like y cubed, or x equal to a multiple of y to any power. So those are often the choices that I make when I'm trying to pick two different paths that get me something. And usually I start with the easy ones and then I work my way down the list if I keep doing the same thing. And if you keep getting the same answer over and over and over and over again, that doesn't mean the limit exists necessarily, but it's good evidence that it might. And then you have to do some other work to try and figure out if it does this, or to come up with a really, really good specific example of a path that makes it not exist. So here, let's see. So I'm going to pick something easy. I'm going to pick y equals 0. To pick y equals 0, I've got the limit as, well, since y is 0, I'm not going to write the y anymore. I'm just going to say the limit is x goes to 0 of 8x squared times 0 over x to the 4th plus 0. But then 8x squared times 0 is just 0. So the limit is x goes to 0 of 0 over x to the 4th. But 0 divided by anything that's not 0, and this isn't 0, because x is approaching 0, meaning it's really, really, really close to 0, but not necessarily equal to 0. I should say, but not equal to 0, not even not necessarily. So this is the limit as x goes to 0 of 0, which is 0. And a lot of the time, not always, when you pick y equal to 0 or x equal to 0, you're going to end up getting 0. All right, we got to wrap things up here. So then we have to pick a different path. Now the problem is, a lot of other paths might actually get you still 0. For example, if you pick y equal to x, I'm pretty sure that still gets you 0. Because then if I do the limit as x goes to 0, 8x squared times x is 8x cubed, x to the 4th plus 3y squared, 3x squared. If I factor out an x squared from the top and the bottom.
Wait, James,
Yeah.
I think is it 8x to the third or is it 8x squared for
X to the
y
third.
equals?
Substituting in y equal to x.
Oh, okay.
If I factor out an x squared, yeah, x squared. Those cancel. You're left with a 0 on top and a 3 on the bottom, which is going to give you 0 over 3 which is 0. So that doesn't help, right? I mean, maybe it helps confirm that the limit is 0, but it's not. So we need to keep trying paths until we give up trying paths and actually try and prove the limit is equal to the number we keep getting, or until we get a different number. Often the thought process behind my choice of how to pick a path is you're trying to make the highest power on the top and the bottom come out to be the same. That's usually my inner thought process. I know that y equals x squared is a great choice here because I'm going to get x to the fourth on top and x to the fourth as the highest power on the bottom. So when you do that, I get the limit as x goes to 0, and I'm going to wrap this up. X squared times x squared is x to the fourth. At the bottom, I've got x to the fourth plus 3 times x squared is x to the fourth. So look what I've got. I've got the limit as x goes to 0 of 8x to the fourth over 4x to the fourth. The x to the fourths cancel, and you have the limit as x goes to 0 of 2, which is 2. But 2 and 0 are different, so this limit does not exist. And that's going to happen a lot. All right, so we're out of time. If you want me to make some videos about some more of this or some other things, I'll be happy to, but you gotta let me know. So send me an email or post something in the post a discussion thread on Canvas, and I will. You speak up first, you get what you want. So you let me know what you want, I will try to make it happen. And yeah, I'll see you guys on Friday. Bye. And thanks for the video. I appreciate you guys showing me your faces.